Hello and welcome to the course Design Borefields with Confidence. This is the third chapter of the seventh part, and we will be talking about the methodology to calculate both the required borefield size and the required borehole depth. Now in the last chapter we discussed the methodology to calculate the required borehole depth, and we figured out that in some cases, we end up with a gradient error because our maximum fluid temperature it crosses the allowed maximum threshold and there is no solution possible. And this also makes it so that when it comes down to borefield sizing, there are actually quite a lot of trial and error involved. You start with a certain configuration, you simulate, you adapt your configuration, you simulate again, etc. And although this is a very helpful process, you learn quite a lot about borefield physics and so forth, and I highly recommend you do that when you're going through this course. It can also be very time consuming, especially when you're in a hurry and you have a very big project and you just need to know, well, what's feasible here. And that's where the calculate required size and depth method comes into view. So this methodology, basically you need to define what your search space is, what area is available and what options, what configurations do I want to consider. So you have to tell the algorithm, this is the amount of meters you have in one direction, this is the amount of meters you have in another direction. I want boreholes between, let's say, 50 and 200 meters, for example. You can say what the minimum spacing between boreholes is, what the maximum spacing is, which configurations you want to consider, and so forth. So it's important to know this algorithm basically searches regular configurations where the boreholes are on a grid, and that's also typically how they are installed in practice. It's not going to scatter the boreholes around in order to find a mathematically optimal solution. So perhaps there is still some room for advancement there, but the current mathematical models that can really place your boreholes all over the field, let's say, they are between 30 minutes and 2 hours of search time. This methodology, just to give you an idea, is around 30 seconds. So we thought that the other more advanced mathematical models are a little bit too slow to be useful in practice, and that's why we stick to the regular grids, at least for now. So given this search space, you have the option to calculate either the minimum total borehole length, so the least amount of borehole of drilling meters, or the least amount of boreholes itself. Because depending on your project, what the optimal solution is, depends a little bit on if you're looking at the borehole meters, or perhaps you have a very limited space and you actually want the least amount of boreholes itself. And the way this algorithm works, it's on the one hand based on an artificial neural network. Now, we already talked about this when we introduced the movie Ellipse. So an artificial network is basically, it's part of the AI group, and it's used to speed up the simulation of certain processes. So we use an artificial neural network to speed up the selection of the different configurations, let's say. And then we use Bayesian optimization, hyperparameter fitting, in order to find which configuration is actually suited. Now, this hyperparameter fitting, it's basically the name of the mathematical problem we're trying to solve here, because there are quite a lot of variables, the number of boreholes in each direction, the depth, etc. And Bayesian optimization is used to optimize the shape, the number, etc. all in one go. And just to illustrate different search algorithms, on the left here you have the grid search. It's, let's say, the most straightforward one. You just say, I want to consider the situations where there are 1, 2, 3, 4, 5, etc. boreholes in one direction with a spacing of 5 meters, 5.5 meters, 6 meters, 6.5, and so forth. And you do that for every variable, and so you end up with n-dimensional grids. And each of the different combinations of all these parameters you simulate, and then you select the ideal situation for all of these. Now, as you can see, because we have quite a lot of parameters to vary, the number of boreholes in one direction, in the other direction, the spacing, the depth, the configuration, this can become quite computationally intensive. and very slow. The second option in the middle is what's called a random grid search, and that's where you do not try every combination, but you just say, I'm going to do a couple of them, and a random algorithm selects which combination you try, and then you again pick the best combination, but there is no guarantee that you actually have found a good solution, let's say. Now, strictly mathematically speaking, it's not possible to be sure that you have the right solution. You can only be more and more sure, but that's a technical detail. With Bayesian optimization, what we do is we start with a couple of random points. We calculate the depth there, and based on that, and based on Bayesian statistics, the algorithm decides where it's the most probable to find a better solution. And we will try again there and there and there until we converge to what's probably the best solution with either the least amount of borehole meters or the least number of boreholes. And just to illustrate how the algorithm thinks, let's say at the Bayesian optimization thinks, let us consider the following graph. So basically what you see here, it's now a two-dimensional situation. We have this dotted line, which is actually the curve we are interested in, and we want to find the minimum for. And what we do is we start with a couple of random dots, in this case 2. We call this observations because it's there where we calculate, in our case, the fluid temperature and the required depth, that we know the solution. We know if we have this configuration, then this will be the required depth, and we know the number of boreholes and the total boreholing. So in these points where we actually calculate the solution, we know what the solution is. And then the further we go away from this, the larger the uncertainty band becomes. And the goal is that in the next iteration, so we're going to make a next observation, what we will do is we will look at this uncertainty graph and we will see or search for the situation where we have probably a better solution. So in our case, we have the dot on the right, the observation on the right. Slightly to the left of it, we assume it can be better. Our uncertainty band goes down, so there is a chance that there is a better solution. So we make an observation and we see, no way, it's worse, and the case is higher. And then we have another best candidate, let's say. And this we iterate for as many iterations as you want until we converge to where is probably the best solution. So this is how the algorithm works. Let us jump into GHE2 with the same example as before and see how the algorithm solves this. So here we are in GHE2 Cloud. I created a new project with the same data we also used in the last chapter. So if you have not watched that, you can watch that, but you also have all the information again in the download section of this chapter over on our website. So we will be working with 0 and 17 as temperature limits, and our borefield section is now completely different. So instead of you having the option to say, well, I want this configuration and etc., you now have your parameter options for the borefield, so you can say which configurations you want, your buried depth and your borehole diameter. These are inputs, they are not optimized. Then you have your minimum and your maximum drilling depth. So the maximum, for example, if you say, well, we have a certain geological, let's say rock at 120 meters, you can say, well, let's not go deeper than that. That's also an advantage of this method when compared to the pure calculate required depth method. We have the minimum maximum borehole spacing, but also the maximum allowed pressure drop in order to make sure that your circulation pump can still handle this and you will not have boreholes that are unfeasibly deep from a pressure perspective. And then on the other side, you have your optimization settings, so you can minimize for either the least amount of borehole meters or the minimum number of boreholes. We will try them both in a second. We have the space available, we have the step size you want to consider. And then we have some 3 parameters that are more related to the optimization itself. The minimum and maximum number of boreholes is basically to speed up your search. It's to say if you have a small project, you can say, well, I expect between 1 and 10 boreholes, let's say. And then it will not search the entire space, so you will converge faster. And the number of searches, it has to do with what we discussed about in just a second ago, when we had this graph and the Bayesian optimization was just switching and finding a better way to, or a better estimate of where the best solution could be. It will limit that number of searches, but typically these parameters are fine for you. Just if you want to dive deeper in the method, you can change these. Let's go ahead and already calculate this. I will also already duplicate this and start the other simulation with minimum number of boreholes, because it can take 30-40 seconds, something like that, for the algorithm to finish. And in the meantime, I want to draw your attention to the flow rate, because this algorithm, it changes the configuration as well, so also the number of boreholes. And if you define your flow rate with the flow rate per borehole, actually what happens is your entire flow rate will also change, because if the algorithm tries something with 4 boreholes or with 10 boreholes, well, the flow rate will be different. And that's not what you want. So you either work with a constant temperature difference in this case, or with a flow rate defined per bore field. In our case, we worked with a constant temperature difference, but this is important to remember when working with this methodology. So let's go back to scenario 1 and to the results. What you can see here, the ideal situation is where we have 9 boreholes of 53 meters, let's say, and we are indeed limited by the maximum fluid temperature. And here in the table below, you can also see we have, in this case, an L shape with 9 boreholes and so forth. So it's all very, very shallow. And that's, also what we talked about with the gradient error. If you have a limitation with the maximum fluid temperature, what you typically want to do is have more boreholes, but as shallow depth as possible. In contrast, if we say, well, let's optimize for the minimum number of boreholes, you see here that we have 5 boreholes of 160 meters deep. And here we indeed have some situation with 5 boreholes, some with 6. And this is a clear illustration that what is optimal can change from your situation to another project, let's say. And this has then 575 drilling meters, and this has more than 100 meters less. So there's a clear difference in the total borehole length, depending on which option you select. Now, just for your information, if you want to work further with a certain configuration here, just double click and it will open a new scenario. Now I want to run another example, now with a clearly more extraction dominated, or I should say without cooling, for example, because here we're again limited by the maximum temperature limit. But just to give you an example where that's not the case, let's go for 8000 DHW, let's say 25 heating, 45 megawatt hours per year, and no cooling. Let us go back to our borefield tab and play around with this a little bit. So let's see, I want everything to 300 meters, but only allow 50 kPa. So let's run this again with the minimum borehole length. And I also will already duplicate this to do the same with the number of boreholes. So this is the result with the case without cooling with the minimum borehole length. And what you can see here is that we now have 4 boreholes with 174 meters of drilling depth. And you can clearly see the temperature goes down. In this case, we are limited by the minimum fluid temperature. If we go to scenario 4, which was the optimization for the minimum number of boreholes, it's also 4. You can see that the depth changes 3 meters, and that's 30 meters, and that's because the Bayesian algorithm, it optimizes, but there is always some randomness involved. But we have more or less the same result here, and that's because when limited by the minimum temperature, typically what you want is just drill deeper and fewer boreholes. And that's a little bit strangey, because we said, well, let's drill to 300 meters, but Actually, it only stopped at 170. And that's probably because the pressure drop was the limitation. So if we go now to make a scenario 5, let's call this 150 kPa, for example. We can go back to the borefield section and say, well, let's allow 150k kilopascals, shall we? And let's optimize the minimum length. Does not really matter. And let's calculate this now again. And probably what this will do is it will force the algorithm to drill even deeper, because now the pressure drop is no longer an issue, and we will end up with fewer boreholes that are somewhat deeper. And indeed, we have now 3 boreholes of almost 200 meters deep. So here 3 boreholes, 4 boreholes, and we see that the pressure drop was just below 100, so the algorithm couldn't find this solution before. Now, as a last variation, what I want to do is I want to work with a DN40, for example, because here the pressure drop is already high, and I want to see if we can go further, go even deeper. So let's go here and say it's a DN40. Going for a larger diameter will decrease the pressure drop of our system and potentially force the algorithm to go even deeper with fewer boreholes. So let's wait just a sec for the algorithm to finish. And this is, for example, a case where saying, well, we only want to 5 boreholes can actually speed things up. But here you see in the results that indeed we now have 2 boreholes with 250 meters drilling depth with 90 kPa in pressure drop. And this is the temperature profile we end up with. So this method can really be handy to play around and just speed things up for you. If you know what you're doing and you know changing the diameter, changing the pressure drop, etc., can force the algorithm to give you a solution you actually want. It's a really powerful way of speeding up your sizing experience. Now in the next chapter, the last chapter of the 7th part, we'll be talking about a thermal response test. It's a little bit out of topic with the last 2 chapters, but what we're doing here basically all depends on these properties. What's the ground data? What's the ground temperature? And there, a thermal response test can be very useful, and we will discuss what it is and how you can use GHGTool to actually calculate and analyze them.